In an earlier section, we looked at this example of an industrial drive shaft and used the maximum stress criterion to be able to come up with the design. And so now we're going to repeat that example using the SciWoo interactive criterion. So if you remember, we wanted a factor of safety of 5. And the drive shaft is going to be made carbon epoxy with plus or minus 45 layers. We want it to be balanced so it can has equal strength if we twist it in either direction. And the torque is 75,000 inch-pounds. The nominal diameter, 6 inches. And so we calculate the loading on that. Inch of xy based on the torque is 1326 pounds per inch. I'm going to shift over to Excel for just a moment. And let's go ahead and change this to be our 1326 inch of xy. And so I've got a tenth of an inch, 45 and minus 45 zeros over here. And the stresses, of course, are calculated down here and plugged into the failure polynomial to come up with the factor of safety. Now, rather than having to scroll down to the bottom all the time, what I've done is copied those cells for the stresses and the factor of safety up here toward the top, so where I can see them very quickly as I change the design. One other thing that I've done here is not really necessary, but I don't like seeing these stresses over here, which really don't apply because the thicknesses are equal to 0. So I want to be able to hide those. And so you notice the note up here I've said, if I put the material code in as 10, then that layer is not being used. And of course, if it's 0, then it's not going to affect the calculations. It's 0 thickness, that is. So if you look here, for example, under sigma 1, I'm going to copy sigma 1 from down here, but I'm only going to do it if this material code is less than 10. So if I do put in 10, it's going to refer to this empty cell I1. And so you can see now, because these two layers aren't being used, if I just put in 10s, it hides those stresses. Again, not a big deal. It doesn't impact the calculations any. I just don't like to see the stresses and factor of safety for layers that I'm not using. So here's the bottom line, though. Here's the stress state. Of course, this one goes in tension. This one goes in compression. And the factor of safety is 7.05. So again, interactive between this compression in the fiber direction and tension in the transverse direction, and again results in this factor of safety 705, the critical one. Okay, let's shift back. Here are the stresses, and again there's the calculated factors of safety. So, because the compression strength is less than the tensile strength in the fiber direction, it makes sense that the minus 45s are the critical layers here. One thing that we should compare this to, if we just looked at the fiber strength, we'd see a factor of safety of 11.8. So there is some interaction here that causes that factor of safety to be lower. In fact, it's kind of an interesting little exercise here, is if I just override that calculated value of sigma 2, remember it's positive, and change it so it's compressive, that jumps the factor of safety way up. Now, that seems pretty reasonable here. If you're compressing it in the axial direction, then when you compress it laterally, it kind of holds the fibers together better and actually increases that strength. On the other hand, if you're compressing it in the fiber direction and stretching it in the other direction, that actually decreases the strength. So that interaction of the two stresses seems to be reasonable. So we can, again, stresses are going to be varying linearly with the load, so we can ratio the thickness. We want a factor of safety of 5. With a tenth of an inch for each, we had a factor of safety of over 7, and so we can ratio that down to get, I think that should have been 707, but anyway, the total thickness of about 0.14 inches. And when we use the maximum stress criterion, it was that thickness was much lower. So again, in a lot of these cases, the stress interactions are really important and really shouldn't be ignored. So one of the variations we did of that problem, we did several of them, but one we did was to say, okay, there's a bending moment being added to the torque. And since we know that plus or minus 45s aren't very good in taking the bending load, m sub x, then we add some zeros to that. And so what we want to do is to find the laminate with the least thickness possible, factor of safety of 5 for all of the layers. Okay, so our n sub x value plus or minus 2829. And remember, we use the negative value. That's because the compression we're sure is going to be more critical than the tension. So minus 2829. Let's go back and add that. Okay, and now I need another layer, so I'm going to shift this back to carbon epoxy. I'm going to put the angle in as 0, and let's just put 1/10 of an inch in all the way across. So right now you can see, well, actually not too far off from my factor of safety of 5, but let's use Solver and do this a little more exactly. Now remember, for the plus or minus 45s, we want them to be balanced. So this thickness is just equal to that one, and this is still going to be minus 45. So the only things I'm going to change are these two thicknesses. So let's go to Solver. And our goal is to minimize the total thickness by changing the thickness of the, by changing the thickness of the 45s and the thickness of the zeros. Now the constraints are much easier to add now that we have a single criterion, the factor of safety, rather than having to look at each individual component of stress. So my constraint, I'm simply going to take the factors of safety for all three of these layers and make them greater than or equal to a value of 5. And let's solve it. So here's what I come up with, a total thickness of a little over 1/4 of an inch, 0.270. You can see that both the minus 45s and the zeros end up with a factor of safety of exactly 5. The 45s are a little bit over-designed, but again, because we have to have a balanced laminate, that's how that's going to work out. All right. So again, there's our thicknesses, total of a little over 1/4 inch. And again, when you looked at what we did with the maximum stress criterion, we got a much lower thickness than that, but probably would not have really had a factor of safety of 5 when we tested that, because again, it ignores the interactions. So now, in these examples we just looked at, though, we assumed that if any of the layer has a factor of safety of 5, that's when we're predicted to fail. And for a lot of applications, actually I'd probably say for most applications, that's reasonable to say if one of the layers is going to fail, that the whole laminate fails. But in the next one, we're going to look at an example of a pressure vessel where that's not going to be the case, and we'll look at what we will call progressive failure, whereas if the resin in one layer fails, doesn't mean that the vessel is going to fail. We'll look at that next time.